Hello everyone, and welcome to my presentation. My name is Giacomo, and I'm going to talk about the Global Myopic Allocation algorithm, or GMA. Together with my collaborators Mark, Marcus, and Adrian, we developed GMA as a theoretical solution to a very practical problem. Therefore, let me now start by outlining the observation that led us to the definition of the distributed path allocation problem, which GMA is a solution for. The starting observation is indeed of very practical nature. Today, more and more interconnected applications require highly available connectivity, and we can see two examples here. The first is the SWIFT network, which carries a large part of global interbank clearing transactions. The second is the Bitcoin network, which is the main example of a distributed ledger and cryptocurrency. Although very different, these two networks have one thing in common. A disruption in connectivity can lead to massive financial damage. To protect against this, they take two different approaches. SWIFT uses lease lines, which provide high reliability but require a centralized operator and are extremely expensive. And the Bitcoin network, on the other hand, runs on the internet, which provides no guarantee at all, but it's of course much cheaper. Moreover, notice that Bitcoin is a decentralized network by design to increase trust, and therefore a centralized solution like lease lines would not apply. This raises a fairly old research question. How can we make highly available communications cheap and convenient in distributed networks? We basically want to reproduce the convenience and guarantees of leased lines on a network by reserving bandwidth on its links. And this reservation is made only for particular flows. This leads to the resource allocation problem, which at its core is a distributed graph problem. We want to allocate a shared resource, represented as edge weights, to particular paths in the network using a distributed protocol or algorithm. This should provide low-cost guarantees and protect against congestion, and also be resilient even in the presence of adversaries. We can see here some older solutions, such as INSERV, DiffServ, and SDN-based protocols. However, as we point out in more detail in the paper, these solutions either use too many resources in the network and therefore do not scale, or require a centralized controller, which we explicitly rule out. Moreover, none of these solutions is resilient to external attacks. One key characteristic of these solutions that I want to point out is that the size of the allocation for a particular path is flexible and can be increased or lowered by communication endpoints depending on their requirements. This also means that the availability of bandwidth to be allocated depends on network utilization. For these reasons, nodes participating in one of these protocols are required to keep a lot of state and keep track of existing allocations to perform admission to new allocations. This also poses security threats, as an adversary can create many such reservations and deplete the available bandwidth for legitimate users, preventing communications and removing any guarantee. But let's now look a bit more in detail at the characteristics of the critical applications we want to address with our resource allocation algorithm, because tailoring our approach to these characteristics will lead us to improving the state of the art. The first important characteristic is that these applications require very minimal bandwidth to operate. Each node requires in the aggregate no more than 100 kilobits per second to function correctly. And this is true, for example, for both SWIFT and the Bitcoin networks. This is a very minimal amount compared to the tens of gigabits per second that modern internet links can provide. However, these applications also need 100% guaranteed delivery, creating a very peculiar combined requirement. Our allocation protocol needs to provide very small amounts of bandwidth with very high guarantees, and even in the presence of adversaries. Our idea is therefore to remove the flexibility of allocation that was present in previous protocols and have a distributed algorithm determine the size of allocations instead of endpoints. This allocation will be sufficient if it's above a minimum threshold. But this small change provides several improvements. First of all, removes the need for bookkeeping and to make sure that the allocations are always available independently of network utilization. And Therefore, it's also great against adversaries because they cannot influence the allocation process. Let's now have a look a bit more in detail how resource allocation in graph works. A graph with resources on edges is represented in the figure. The resource is a non-negative edge weight that is associated with every edge and of varying amount, as shown by the thickness of the lines. We assume that there are nodes that want to communicate and want to do so by connecting through paths. On each of these paths, we will have an allocation. We do not restrict the shape or form of the paths, and we allow paths with loops. Now, each of these paths, as said, requires a certain amount of resource. You can think of bandwidth for communication. And this resource is allocated to a path and cannot be used for other paths. So if we zoom in into this central link and represent the total available resource of the link by this rectangle, we see that the paths that traverse this link have each a certain defined amount of bandwidth. Now, the first property, of course, that we want from our resource allocation protocol is to never have overallocation. That is to say, never have the total sum of resources crossing a link exceed the resource of the link. And this is even if all paths that can traverse that link or edge are receiving an allocation. Now, the first property we have already outlined is this non-overallocation properties. But motivated by our practical problem, we have many more properties we would like to achieve. The second one is that no global coordination is required. As we saw before, the Bitcoin network, for example, requires decentralizations to build trust. And we express this by the requirement that only path local nodes participate to the computation. Then we would like to have the largest allocation possible globally to maximize the usefulness of the network. We would like every possible path to get a small but useful allocation. We would like more popular paths to have bigger allocation, and this popularity we will express in a formal way later on. And then we want, of course, to have an efficient resource allocation procedure, which is fast for some definition. Now, we can group these ideal properties. The first two are core properties, which compose the definition of the distributed path allocation problem, which is formalized in the paper. And then there are the other properties that are additional nice properties that make the algorithm even more suitable to solve our initial problem. Now, these are hand-wavy definitions we've given so far. Now we will start adding more and more formal definitions to this problem to see how we can solve it with our theoretical GMA algorithm. Now, to do so, we need to start by defining allocation graphs. We see here on the left a communication network as a graph, where nodes are forwarding elements and edges are links. Again, we have a resource on each edge, which is a non-negative weight that represents, for example, bandwidth. But we also see here that there's a local substructure to the node, and this represents the local view. As we said before, each node has, for example, preferences, and this is expressed by this local view. Now, more specifically, each node has interfaces, which are the attachment points of edges, and a local interface, which represents the local traffic source. If we zoom in on a single node and we look at the interfaces, which are here denoted by I and J, we have that an interface pair is connected by a pair allocation, which is highlighted here in red. And the semantics of this pair allocation is that it represents the maximum amount of resource that paths transiting from I to J can have in the aggregate. And it therefore is the way to express the preference of the node we were talking about before. Now, of course, we want that the sum of outgoing pair allocations from an interface has to be lower than the resource of the attached edge, and we call this sum the divergent of the edge. Similarly, we want the sum of incoming pair allocations to an interface to be lower than the resource of the attached edge, and we call this aggregate sum the convergent of that interface. These pair allocations can be naturally represented as allocation matrices. Entry ij in the allocation matrix represents the pair allocation going from interface I to interface j. Then naturally, the sum over columns becomes the convergent of interfaces, and the sum over rows is the divergent of interfaces. And we have each node in the network have such an allocation matrix. Now we can therefore define the allocation graph as a regular graph with nodes and edges, but with each edge associated with a resource and with each node associated with an allocation matrix. And we're now close to defining the path resource allocation problem. We just have to define what a path is and what an allocation is. In an allocation graph, a path is a sequence of interfaces that must start at a local interface and end at local interface. You have two examples of a path here in the figure. An allocation is a certain amount of resource that is assigned to a path and cannot be assigned to any other path. Therefore, the path resource allocation problem is to find an algorithm, A, that allocates the resource to any path in an allocation graph. Of course, it has to do so respecting all the properties we've been talking about before, and which we can now formalize in more detail given our definition of an allocation graph. The first property is to never get over allocation on any link. And this can be easily formalized by saying that the sum of allocations for the paths that traverse a certain link can never be larger than the link resource. And this is even if there is an allocation on all possible paths. The requirement for no global coordination is expressed by the locality property, which says that this algorithm for a path pi is a function of the on-path allocation matrices only. The idea that the allocations should be the largest possible is represented by this notion of Pareto optimality, with which we express that no other algorithm can trivially improve the allocations of our defined algorithm, and we will specify this property a bit more in detail later when we will show a sketch of the proof of this Pareto optimality for the GMA algorithm. The requirement that every path gets some allocation and this allocation is useful is presented in two ways in the paper. The first part of the requirement is given by the usability property, in which we have that for any path, the allocation must be positive. And its usefulness is shown in simulations to check whether the results of this allocation are above a certain useful threshold in real-life communication networks. You can find more details about the simulations in the papers, but in the interest of brevity, I will not discuss them in this presentation. We further want popular paths to get bigger allocation. And this is, again, a very practically motivated requirement. We express this by the monotonicity property, which says that increasing the pair allocation for a node on a path pi cannot decrease the overall allocation. And finally, we want allocation computation to be fast, and this is expressed by the efficiency property, which says that the algorithm must have at most polynomial complexity in the input size, which is the sequence of allocation matrices by the locality property. The search for a solution to the distributed path allocation problem leads us to the Global Myopic Allocation algorithm, or GMA, which you can see here on the slide. GMA can compute an allocation for any path on the graph, starting only from the convergent, divergent, and pair allocation of the nodes on the path. And we therefore see that already from this formula that it has linear complexity in the input size. Not only that, but it also checks all the boxes for the properties we required and formalized before. We prove that it achieves all these properties in the paper. Amongst all other properties, I would like to show you how we defined and proved the Pareto optimality property for GMA. Now, the full definition of what Pareto optimality is in the paper, but intuitively, we have an algorithm A to be Pareto optimal if no allocation it provides can be increased by, for example, another algorithm without either causing overallocation in some graph or reducing some other allocation. And this is all over all possible graphs. And we prove that GMA is optimal by contradiction. We assume that there is an algorithm B that improves over the allocations that GMA, here represented by algorithm A, can provide for a certain path on a particular graph. Then we transform the graph by removing all nodes that are not part of the original path in which B has a higher allocation than A, and replacing them with stub nodes that only attach to the nodes on the path, therefore reducing the original graph to a tree. And it's really important to see here why we do this construction. With this construction, we have a new graph, which is a tree, that has a path in it that is exactly the same path to the level of allocation matrices. That's why we need these stub nodes. All other paths, however, are different. Now, from this construction, we can show that for this particular path in this new graph, either there is another path for which the algorithm B has a lower allocation than A, or B is an algorithm that over-allocates and therefore violates our assumptions. And very interestingly, we do this by showing that there is a pair allocation represented in this graphic for which the algorithm A achieves full utilization. Therefore, GMA can fully utilize one of the pair allocation in this path, meaning that the sum of the allocations over that pair allocation reach exactly the pair allocation itself. Therefore, if the allocation for that path in B is higher than A, it is either over allocating or there is another path passing through that pair allocation that needs to have a lower allocation. So to summarize, we've just shown that there is no algorithm that can be better than GMA on all possible graphs, because we've shown that if there is an algorithm that is better and provides better allocation than GMA on a particular graph, then we construct a second graph in which this particular algorithm needs to have a lower allocation than GMA, or it must not meet the requirements for non-over allocation. Now, let me give you a brief outlook of the future work we want to do in this space. We're already working on a definition of fairness for our algorithm that is based on the notion of allocation matrices. We want to study the global optimality and not just the Pareto optimality of the algorithm, maybe showing that GMA has some global properties that it achieves. For example, it maximizes the sum of allocations for paths or something along these lines. And finally, we would like to construct a resource reservation protocol based on GMA allocation. And this is already done, and it's already been published at WQS 2021. So if you want to know more about this, please have a look at our paper. In conclusion, in our paper, we propose a new take on an old and hard problem, which is the graph resource allocation problem. And our new idea is to study it for critical applications, which have very minimal bandwidth requirements. These minimal bandwidth requirements remove the need for allocation flexibility and enables us to have the network establish these allocations rather than the endpoints. Then we define the allocation graphs, which represent a distributed network with policies or preference given by allocation matrices. And finally, with these elements combined, we define the distributed path allocation problem. We propose also a solution to this path allocation problem, which is the Global Myopic Resource Allocation algorithm. This algorithm provides an allocation to any path never over allocates, meaning that the sum of the allocation is always smaller than the link's resource, and it respects the policy. We also show it is Pareto optimal, meaning that it cannot be trivially improved. And with this, I thank you very much for your attention. Please get in touch if you have any questions or comments on our work and our presentation.